Welcome to 5.5. This is indefinite integrals and substitution. And two things that I just want to talk about briefly is this. I'm going to try to go back and work out some of the proofs on the whiteboard. So hopefully you guys will be able to see the whiteboard. And I'll go through these notes as well, but we'll see how this works. So indefinite integrals as opposed to definite integrals, indefinite integrals don't have bounds. Like in 5.4, we had definite integrals, which are giving us the area underneath the curve. An indefinite integral, like we have right here, that doesn't have bounds, is just going to give us an antiderivative plus some constant. So we always need to remember to add the constant on that. So this is going to equal the antiderivative, which is basically saying here, if we take the derivative of this function right here, we get this little f in there back. Now, substitution is going to be one of the first methods that we use to solve indefinite and definite integrals. And I'm going to tell you this, like, this is how we undo the chain rule. And if you remember in Calculus 1, how like the chain rule is pervasive and does everything from here on out, like U substitution is everything from here on out. Like if you're not doing U substitution in a problem, there's a good chance that you might be doing it wrong. So recall really quickly, and I'm going to try to switch over to my headset because I can hear the kids yelling. So if you recall, the chain rule takes the derivative of some function. If we have u to the n plus 1 over n plus 1, well, we're going to use the power rule on this. So we're bringing down the n. We're bringing down the n plus 1. And then from that gives us u to the n. And then we have to take this times the derivative of u with respect to x. So that's what our du dx is. So really, if we have the integral of u to the n times the derivative of u with respect to x dx, this is going to give us back to u to the n plus 1 over n plus 1 plus c. Now, this is the other way to think about it, which I think is a little more intuitive. If we have a composition, because we're called the chain rule, we work on compositions, then the composition ends up being, if we have this dx on the inside, and we have the derivative of g on the outside, well, this could be rewritten in terms of things. But if you think about this, this is going to be some antiderivative. And if we take the derivative, of this, we're going to get this back down. So here, I'm going to try to toggle the whiteboard to give you an idea as to what we're doing. And I'm going to stop sharing here, but start sharing on the whiteboard. So I'm going to prove these a couple integrals really quickly, and then you can take my word on the rest. So let's see. Okay, so if we have the indefinite integral of sine of x dx, oops, excuse me, it's not that, and look back at my other screen. If we have the indefinite integral of tangent of x dx, we don't know what the antiderivative of tangent is directly, but we know that tangent is sine of x over cosine of x dx. Now, we don't see this as a composition, but like we can think of this as the integral of sine of x times 1 over cosine of x dx. Now, if we think about this in terms of the more complicated function, this right here is the more complicated function. And more to the point, if we take the derivative of this, well, this is going to give us a sign, but not quite the sign, to give us a negative sign. So what we're going to do is do a u substitution. So the way we do that is we let u equal cosine of x, okay? Now what we're going to do is take the derivative of this. So the derivative of this, du dx, equals the derivative of cosine is negative sine of x. Okay, or more to the point, we could write this as du equals negative sine of x dx by splitting up this differential here. Now, when we have this, notice, we have kind of like this piece right here. We need to get this negative over here. So we could really say that sine of x dx equals negative du. So we have a sine of x dx. For that, we can substitute negative du. Additionally, because we know that u equals cosine of x, we can write this as the integral of. Now, once again, this piece right here is giving us a negative du. 1 over cosine, that's going to be 1 over u, because we're just plugging that in. Now, if we think about what's the antiderivative of 1 over u, well, that's going to be the natural log of the absolute value of u. So this right here is going to be equal to the natural log of the absolute value of u plus some constant c. The other thing is that negative is going to have to pop out here, and that's what we have. Now, we took the antiderivative, or the indefinite integral, of this with respect to u and not x. The original problem, if we look back to here, we want to know what this is in terms of x. So we have to back substitute now. So this right here, we're going to take this, plug it back in there. So this is going to equal negative natural log of the absolute value of cosine of x plus some constant c. Now, if you remember the log rules, this can come up and act as an exponent for this. So this is the same as the natural log of the absolute value of cosine of x to the negative first power plus some c. And this is really a 1 over cosine. 1 over cosine is a secant. So this is going to be equal to the natural log of the absolute value of secant of x plus some constant. And that is how you do a u substitution, and that is what the antiderivative of tangent is. So let me get back to the notes really quickly. So when we come over here and you see that's what that proof is. Now, you can take my word that the antiderivative of secant of x dx, the natural log of the absolute value of secant of x plus tangent of x dx. And I'll do that. And basically, I'm going to work through that problem, doing a little u substitution. It's pretty tricky. We're going to do some easier ones here in a minute. And then the proofs of cotangent and cosecant basically follow from the proofs of tangent and secant, much like trig functions. If you can take the derivative of one, you know the derivative of many. If you can take the antiderivative of one, you can figure out the antiderivative of many. So stop sharing here, get back to the whiteboard. Hopefully you'll be able to see the whiteboard. Okay, so let's get to the next page. Now, here, if we're going to find what is the indefinite integral of secant of x dx. Okay, first thing that's going to be super counterintuitive is we need to multiply this by a fancy one. And when we multiply this by a fancy one, the fancy one that we're going to use is going to be this. Secant of x plus tangent of x all over secant of x plus tangent of x. Now, this is one, and I wouldn't expect you to come up with this on your own. But when we do multiply this through, what we're going to get is, and I'm going to distribute this secant to that secant into this tangent. We're going to have the integral of secant squared x plus secant tangent. And this is going to be over a secant of x plus a tangent of x. And this is all dx. Okay, so I know this is kind of a mess right now, but just roll with it for a second. Now, you always want to make the thing that's harder to get your u, and like you can never get derivatives. It's hard to get derivatives to be on the bottom. So if we let this be our u, that is u equals secant x plus tangent x, and we take the derivative here. Now the derivative of u we can just say is du. The derivative of secant is secant x tangent x. The derivative of tangent is secant squared plus secant squared x. So we took the derivative of each of these individually. This is going to be a dx. Now we can see that if we look back at our indefinite integral over here, we have a secant squared of x plus secant tangent of x. So that can be our du. This right here is our u. So rewriting this integral in terms of u's and du's, this, everything on the top is a du. because we have a secant tangent plus a secant squared, which we have right up here. We have a dx, which we have right here. So this is just going to be a du. This is our u, d over u. And we can think of this really as the integral, the indefinite integral of 1 over u du. Well, this, once again, the antiderivative of 1 over u is the natural log of the absolute value. So this is going to be the natural log of the absolute value of u plus some c. We took this original indefinite integral in terms of x. We need it back in terms of x. So we do a back substitution here. So we're going to plug this in for our u. This is going to be the natural log of the absolute value of secant x plus tangent x plus some c. And you'll notice that if we get back to this right here, in fact, it is. So the indefinite integral of secant x dx is, in fact, the natural log of the absolute value of secant x plus tangent x plus d. Now, that's usually something people memorize and don't derive each time through, but that's what's going on. So I'm going to talk through some examples really quickly. And I'm not going to use the whiteboard as much here. We'll be using the whiteboard in class, but like, hopefully we're going to talk through what the logic is in the problems. And because these aren't trig problems right off the bat, probably going to be a little bit more intuitive and easy for you to understand. So excuse me. I just want to make sure that we're recording. Okay. So when we're over here, we look at this indefinite integral. It would be indefinite integral of 3x plus 2 in parentheses. Then over here, we have 3x squared plus 4x all to the fourth power dx. Now, looking at these two, it's pretty easy to figure out what's the most complicated function. The one on the right is more complicated. You rarely let u be the whole thing. It's always the inside, because we're thinking about this in terms of like undoing the chain rule, which is undoing composition. So if I let my u equal 3x squared plus 4x, we have it right here. If we take the derivative of u is du, the derivative of 3x squared right here, bring the 2 down, subtract 1, so it's 6x squared. Derivative of 4x is just 4 dx. Now, it doesn't seem like that we have this exactly over here, but we do have a 3x plus 2. So if we see there's a factor of 2 in here, we can factor that 2 out, divide by it. Now, what we have exactly is our 3x plus 4 dx. So this and this, we can substitute with the du over 2. That's where this is coming from. When we plug this in for our, right here in the fourth power function, that gives us our u. This right here is much easier to take the antiderivative of. Now, this 1/2 can slide out to the front. So we have 1/2 times the indefinite integral. So really just the antiderivative of u to the fourth. And this should be a du, sorry about that. When we have these powers, we can just add 1 and divide by that. So when we add 1 to our 4, we get 5. Dividing by that 5, we get this. That 4 and 5 multiply together to get this 20. We want to get this back in terms of x because the original problem is in terms of x. We do this substitution back into that u right there, and we add our constant c. That right there is a classic u substitution problem. So this next one, if we look at this, and there should be a dr at the end of this thing right here, sorry about that. If we have the indefinite integral of 9r squared all over the square root of 1 minus r cubed, well, the more complicated function is the one on the bottom. Once again, you don't want to let your u equal the whole thing, just what's inside that complicated function. So if we let our u equal a 1 minus r cubed, we take the derivative of this, the derivative of the constant 0, bring the 3 down, subtract 1. So our du equals negative 3r squared dr. Now, if we look at the top, this 9, we don't really need the 9. Constants are like, we can just mess with those later on. But we do have an r squared, and there should be a dr right here. So r squared dr is going to really be a du over that negative 3, which we've substituted there. What's left over is we have that 9, which follows down here. We plug this in for our u. So 9 over the square root of u times du over negative 3. And that's how we've done our first u substitution. Now, the 9 divided by the negative 3 gives us that negative 3 out there. And really what we're left with is we have this 1 over the square root of u du. 1 over the square root of u is, 1 over u to the 1/2 power. When we bring this up, it's going to be a u to the negative 1/2 power du. Once again, to take the antiderivative of something like this, add 1 and divide by that. So when we add 1 to negative 1/2, we get positive 1/2. When we're dividing by 1/2, we really multiply by the reciprocal. So multiplying by the reciprocal of 1/2 is 2. 2 times that negative 3 gives us negative 6. We've taken the antiderivative. That's why our integration, our integral sign goes away. And then the last thing is this is in terms of r. We want to get it back in terms of r. All we have to do is back substitute that in for our u, which we can do. 1/2 power to the square root. So negative square root of this thing, our u, plus some constant c. And that's what we have going on here. So we want to evaluate these integrals. And here what we have is we have the square root of sine times cosine of 3x dx. And once again, like, I wouldn't expect you to get this right off the bat, but taking a look at it, what we're going to have to do is this. Now, cosine cubed, we could think of that as a cosine squared times a cosine. And if you think about it like this, we can think of sine, the Pythagorean identity, sine squared plus cosine squared equals 1. Really, we can solve that and move it around and get 1 minus sine squared x for this cosine squared. Okay, so when we do that, the one thing you can notice is like the most this is complicated, that's complicated. Here we're going to do something a little counterintuitive. But if we take our u to be sine, the derivative of sine is cosine. So that's how we do this. So if we let u equal sine, derivative of u, du equals cosine of x dx. Okay, now we have a cosine and we have a dx. So that right there will give us our du. This is going to be a sine to the 1/2, which will just be a u to the 1/2 by the substitution. 1 minus sine squared, well, 1 minus sine squared is going to be, the u's going to be right there. And really at this stage right here, I've distributed this into 1, I've distributed this into this piece right here. So after we have that, we can do our u's. With our u's right here, u to the 1/2 power, to take the antiderivative of that, we're adding 1 here to get that 3/2, dividing by 3/2 gives us 2/3. This here, really, we should have multiplied that sine to the 1/2 times that sine squared. That should be a sine to the 1/2 plus 2. But let's just run with it like this. Sorry about that. It's I did this PDFs and I can't really change it right now. But if we're doing this, we're really adding 1, dividing by that, we get this. Once we have our plus c, our constant, we always want to do a back substitution. U comes down here and our signs from there. And then that's how we're doing it there. So a couple more, and we have this. If we have cosine of the square root of theta all over the square root of theta times sine squared theta, that's sine squared times the square root of theta, like, you think of this as the sine of the square root inside of something squared, which that to me is the most complicated thing. And you want to move one step in from the outside. So let me just I'm gonna get this. Let's get to the whiteboard. I'll just kind of show you how I'm thinking about this problem. So let's say we have the integral of cosine of the square root of theta all over the square root of theta, sine squared of the, so we have sine of the square root of theta, but the sine's being squared, so we really think of this as being squared. So we're going to kind of like, what's the most complicated thing? Well, cosine of the square root of theta is pretty complicated. The square root of theta is pretty complicated, but sine of the square root of theta squared is most complicated. And you always want to move one step inside of the most complicated function. That's going to be our u. So if you let u equal sine of the square root of theta, well, here our du, we're taking the derivative of that side. The derivative of sine, using the chain rule going from outside to inside, cover up this. Derivative of sine is cosine of that thing. So we have a cosine of the square root of theta times. Now, because the square root of theta is theta to the 1/2 power, the derivative of this right here is going to be 1/2 theta to the negative 1/2. which we could think of really as 1/2 times 1 over times 1 over the square root of theta, or theta to the 1/2. So this piece by the chain rule is going to be on the end of this. So we're going to have a 1 over 2 square root of theta. We're kind of simplifying this. Our du is going to equal cosine of the square root of theta all over 2 square root of theta. Now, if we look back at the original problem, this up here, we have, oops, and I should have, there really needs to be a d theta on the end of this, and there needs to be a d theta, excuse me, d theta, d theta. Now we have like all of this. We have a this, we have a that, we have a that, we have a that. This squared is attached to that. So we don't have that 2. So I'm going to move this 2 over and say 2 du equals cosine of the square root of theta all over the square root of theta d theta. So what I can do is this. Now, this is going to be our u. So this right here is now a u. So, and that u is being squared. So 1 over u squared. That's definitely that. Now we have this piece. This all right here is this all right here. So we can just substitute in for that a 2 du. Once again, the constants move to the front. So 2 comes out in the front. 1 over u squared is really u to the negative second power du. So we can now apply that, add 1, divide by it. Now, when we add 1 to negative 2, we're going to get u to the negative first. When we divide by that negative 1, we get this. The constant pulls down. We have to add a constant. So simplifying this a little bit, this is going to be the same as negative 2. This u to the negative first, we can now put in the denominator over u plus some c. And the last thing we have to do is just get this back in terms of theta. It was originally in terms of theta. Bring that, substitute it in for our u. And this is going to be negative 2 over the square root of sine of the square root of theta plus c. And I know, like, this is tricky. This is a hard problem, but if we take the derivative of this, which I'm not suggesting that you do, you're going to get this back. There's always that little check, because this really is the antiderivative of that function up there. So hopefully that makes a little bit of sense. We're going to get back to the PEF notes. And then looks like there's a couple more examples. Now, the next one, we have the natural log of the square root of t all over t, which really we could think of this, and there's going to be a little bit of like log rules that are going on here. Now, the square root of 1/2 power, so the t is raised to 1/2 power. The log rule says that we can bring the 1/2 in front, so a little bit of algebraic manipulation on these can go a long way. Now, if you look at this, we can pull that 1/2 in the front. Now, I know I said that most of the time it's in the u is going to be in the denominator, but if we think about what's the derivative of the natural log, it's 1 over t, no, the derivative of the natural log of t is 1 over t dt. So I'm going to pick it up right there. Let's see if we can, hopefully we can see this stuff. So here, if we have 1/2 in a row, the natural log of t over t dt, well, you can always, like, the worst thing you can do is do nothing. If you let u equal t, u equals t, the derivative of that would be du equals dt. That's really going to give you the integral of the natural log of u du, which is great if you know what the antiderivative of the natural log is. But like, we don't, because we don't know what, like, we need to know, hey, the derivative of what's the natural log. We don't know that. That's going to take some more machinery and like a further section for us. So this right here, not going to work out for us. Didn't work out. So next thing you'd be is, well, let's try the numerator. U equals the natural log of t. Our du is going to equal 1 over t, the derivative of the natural log of t, then a dt. Well, good news, we have that piece right there. So this is 1/2 integral of, now this whole thing was our u, right? This whole thing is our u right there. So there's going to be u times our du. Now remember, that's u to the first. When we take the antiderivative, we're going to add 1 to this right here and divide by that. So our 1/2 from there carries down. We're going to have a u squared divided by 2. plus some constant c. Do a little bit of substitution because we want to get this back in terms of t. The 1/2, the 2's really multiply together. This u is natural log of t. So the natural log of t squared over 4 plus some constant. This right here is the antiderivative of that thing right there. And I'll stop sharing. Let me get back to the notes. And that's exactly what we have over here. Okay, so coming down, there's only one problem that we have left. This one, like, I'm just going to do it on the whiteboard because it may be intuitive, maybe counterintuitive. It's like, it just is following kind of a formula, but there is a bit of abstract thinking in factoring. It's not so much use substitution as getting back to like using an algebraic techniques to get things simplified before we move on. And I want to show you how that would work. So if we have the integral of 5 over 4 plus 9 plus 4r squared dr. First thing, we can pull this 5 through. Second thing, like, I know this is going to be weird, but like, this is something that's going to have to stick with you. But if you have derivative of, let's say, let's do this. Let's say y equals tangent inverse of x. And I don't expect you to memorize, or I don't expect you to have this like committed from memory from 4 weeks ago, but like you're going to have to put it in your memory basket. Now, dy dx, the derivative of this is going to be 1 over 1 plus x squared. It's the derivative of the tangent inverse. If something's in here, we have to use u sub, or we'd have to use the chain rule on that. Now, anytime I see number over number plus like variable squared, it's always going to be a tangent inverse. It just is. So I'm going to factor some stuff out. In fact, I'm going to factor a 5 out. I'm going to factor a 9 out. Now, factoring the 5 out of the numerators, I don't think we're not getting real tricky with that dr. Now, this right here, factoring the 9 out, that's going to give us a 1, but there's no 9 here. So we really need to think about multiplying this term right here by a 9 over 9. When we do that, yeah, of course, that 9 and that 9 can carry out. We have this plus 4/9 r squared. So, like, I'm going to write this a little bit differently. This is really going to be 5 over 9 integral of 1 over 1 plus 2/3 r squared dr. Now, if you think about this, this would have a 2/3 in it to get us our 2/3 being squared down here. And then we'd have to multiply this by 2/3. To compensate for that, since we don't have it, we're going to have to multiply this by the reciprocal of that, or divide by this. So this is really going to be 5/9 tangent inverse of this thing, 2/3 r, divided by 2/3 plus c. Can we do this? Reciprocate that. Now the 2 is going to up number the denominator, but this, when it flips over, is going to cancel with one of those. So when we get this, do this real quickly, 3/2, 3/2, multiply this by that, that's going to give us a 3. So this is the end result here is going to be a 5/6 tangent inverse of 2/3 r plus c, and that is that one right there. So if you look back with my 3rd grade handwriting, yeah, it is a 5/6 tangent inverse of that. Hopefully, I know this stuff's tricky. Look at this. We'll do more examples in class, and best of luck, and we'll see you soon.